Okay, we go back into section 7.2. We'll do the second half today. We're going to talk about the sampling distribution of a difference between two proportions. So let's say at school 1, 70% of the students did their homework last night. So we're going to identify P1, the proportion of 1 is 0.7. As we go here, let's get this clicked on. There we go. At school 2, only 50% of the students. So P2, population proportion of 2 is 0.5. So the counselor at school 1 selects a simple random sample of 100 students and records the proportion that did the homework. All right, school 2 does a simple random sample of 200 students and records the proportion that did the homework. So we can kind of see here that the population or treatment, that's 1. That's 2, and 2, and then of course the parameter P1 statistic. Okay, remember that's when we do our sample, that's P hat 1, and then the sample size is N1. So we'll use those subscripts to identify which one it's from. All right, now as we look here with the shape, we're going to be approximately normal because, we kind of take the n times P is going to be greater than 10, which of course n times 1 minus P in both cases is also going to be bigger than 10. All right, so their centers, of course, are going to be the means of each one, the population means. And then the variability, we take the population proportion of success times failure divided by the sample size, and then take the square root. So we have both of those. And because 100 and 200, those are less than the 10% of all students at both schools, we're assuming that we're in that 10% condition that we talked about before. So we're all good on all those things. Now, what can we say about the difference between those proportions? Well, the thing is we have different sample sizes, so that's why it's good to use a proportion. And simulated sampling distributions of the difference in sample, that's what we get here. So a wide range of course, difference in proportions that we'd have. Now, one set of samples gave P1 at 0.72 and P2 at 0.45 or 0.47. So the difference between those is 0.25, which is illustrated right there with the highlight there. All right, so again, we're just kind of talking about that. Now the mean, of course, is right in the middle there. It's 0.2, so it's basically the difference between the two, 0.7 minus the 0.5 is what we see there. Now the standard deviation, interesting. What we have to do is take the standard deviation of each one, add them together, right? And then what we're going to do is we're going to then take the square root of that. So that's how we do those for the standard deviation of the difference. Remember, back before you think you'd subtract them, but actually you add them is what you do to find those. All right, so basically when you choose a simple random sample of size N1 for population 1, proportion of successes is P1, and the independent simple random sample of size N2 from population 2 with proportion of success is P2, then here's what we know. We know that they're going to be the difference is going to be approximately normal as long as the large counts condition is met, where, you take the sample size times the proportion. It's got to be bigger than 10. Sample size times the probability of failure is also bigger than 10 in both cases. And then the mean, of course, is just the difference between the means of the populations. So again, we take P1 minus P2. Standard deviation, again, we're going to find the standard deviation of the populations in each one, and then add them together and take the square root. And again, as long as the 10% condition holds true, we're all good on all those. Formulas hold true. Okay? So again, formula for the standard deviation exactly correct when we have two types. It's got to be independent samples, so we can add the variances. And it's got to be independent observations within each sample. When sampling without replacement, the actual value of standard deviation is smaller than the formula suggests. So as long as that 10% condition is met, then that difference really isn't important. So we're okay. We've talked about that many, many times now. All right, so here we go. Teacher brings 2 bags of colored goldfish crackers to class. Bag 1 is 25% red crackers. Bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. So using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a separate simple random sample of 40 crackers from bag 2. Now, P hat 1 minus P hat 2 is the difference in the sample proportions of the red crackers. Now, what is the shape of the sampling distribution? Well, remember, it should be normal, right? Because if we take the sample size times the proportion, 50 times 0.25, yeah, and 50 times 0.75, it works. And then if we do for the second one, we don't really do a sample size of 40, but 40 times 0.35 and 40 times 0.65, those are all bigger than 10, so we can assume that we have a normal distribution. Now, finding the mean is simply just taking the proportion of the first bag, which is 0.25, and minusing the second one, 0.35. So we get a negative mean of 0.10. All right, and calculate interpret and the standard deviation of the sampling. All right, so if we do that, we can use that formula where we can take the 0.25 times the probability of success there of 0.75 and divide it by 50, and then we can take 0.35 times 0.65. So basically, it's the probability of success times failure divided by your sample size. We're going to add those together, take the square root. So what we're saying here is that the difference from bag 1 to bag 2 in the sample proportions of red goldfish crackers typically varies by about 0.097 from the true difference. We call that the true difference because that had populations. And so we're talking about the true difference in proportions of negative 0.1. All right, so there we go. That's a good little problem there. Now, again, estimate the probability that the proportion of red crackers in the sample from bag 1 is greater than the proportion of red crackers from bag 2 in the sample. Well, really what we're doing is we're trying to say the difference between those is greater than 0. So our actual value, what we're going to do is we're going to figure out it's 0. And what we're going to do is we're going to subtract the true mean, negative 0.10, divided by that standard deviation that we figured out. Okay, so what we have to do is figure out the probability that z-score is greater than 1.03. So this is one of those cases where our z-table shows us what percentage is below. So what we'd have to do is we'd have to find that percentage and then of course subtract from 1 if we want the proportion or percentage that's above that. So if we did that correctly, we would find that we would have 0.1515, 15.15% is that probability. So interesting problem. So again, look through those exercises. Some practice with those. Repetition is really key with all of this on getting comfortable with what these questions ask and how to figure those out. So go ahead and do that. Again, these are all of the things from section 2 that we should be able to do. Again, the key thing is interpreting those correctly and be able to pay attention to the verbiage on those problems. And again, check those solutions with those that are posted and kind of pay attention to how it's being stated when it says interpret. So that's really important. So those things should all have, hopefully get some practice and solidify those. And then we'll move on to the last section, section 7.3. Until then, I'm Mr. Boone.